Hello and welcome to a GeoDict tutorial. This video was created by Andreas Grieser, Business Manager for Image Processing and Image Analysis at Math2Market. My name is Sina Schwichow and I will show you in the following video how to model an artificial eardrum made by electrospinning using our fiber generator module FiberGeo. We would like to thank the Ear Research Center of the University Hospital Dresden and the Institute for Textile Machinery and High Performance Textile Materials of the TU Dresden for providing us with this SEM picture that you see here. We will first analyze this image and then we will generate a digital statistical twin. This will allow us to perform simulations for property calculations based on the identical statistical material properties. This helps us not only to test the existing material, but also to improve it. To import the SEM image into our software GeoDict, we first need the module Import GeoVol. For this purpose, we click on the button Import in our menu bar and select Import GeoVol. On the side, the view of FiberGeo changes to Import GeoVol. Using the Browse button, we select the image and import it with a voxel length of 1 micrometer. We will define the exact voxel length later. After we click on Import, the Import GeoVol main window opens, where we can edit and modify the SEM image. Our final goal is to segment the image and then determine the orientation of the fibers. We will first switch to the Stacked View mode under View mode. Since this image is a 2D image, we look from the Z-axis in the direction X and Y, since only these two axes contain image information. To better determine the orientation of the fibers, later on we have to segment this image with GeoDict. Since it is a SEM image, it is not easy to segment the fibers. On the one hand, there is a gradient in the depth of the image, and on the other hand, there is only one 2D slice on which we can work. This becomes particularly clear when the current segmentation is varied and made visible using the currently set threshold under Threshold Visibility. That's why a little manual work is required here, and you can't just use the fully automated ODSU segmentation under thresholding. As you can see, a lot of fibers are lost here, so we have to reduce the threshold a bit. This also allows us to segment the fibers that are in the background. Of course, you can now clearly see that the fibers in the foreground, where sometimes several fibers are parallel, are melting together. However, since we only want to analyze the orientation of the fibers, we can ignore this at the moment. With this threshold, we should get a useful result. By clicking the Import Image button at the bottom, the segmented image can be imported into GeoDict. As you can see, a so-called GeoDict Result Viewer window opens, where you can see the parameters that have been set listed again. Since GeoDict is in the 2D view in X direction, we have to change it under camera direction to Z direction. Here we can see the fibers as we have segmented them. And very importantly, we can see the scale bar up here as well. We will now use this to determine the correct voxel length. We zoom in a little further. Since we know that this scale bar is 50 micrometers long, we can tell GeoDict here to change the voxel length so that the section we measured is exactly 50 micrometers long. The voxel length has now been adjusted accordingly. First, since we want to analyze the orientation, we will now remove this bar with the meta information that was contained in the image. To do this, we go to the 3D view, select Process GeoCrop, Activate the preview and lower the Y value so far that we only cut away the bar with the meta information at the top. Now we only have the fibers in the image and can perform the fiber orientation analysis in the FiberFind module. Therefore, we select the module FiberFind, the function Estimate Fiber Orientation, and click on the Edit button. Here we can divide these structures into several subblocks, for each of which we can get an orientation tensor. In our case, we are only interested in one. For the algorithm, we keep the star length distribution because it also works in 2D. With a click on OK and then on Run, I start the analysis. GeoDict now calculates the orientation of the fibers in our image. We can use the results later as an input parameter for FiberGeo. Now we have here an orientation tensor which we will use later. To create a model of the eardrum, we select the module FiberGeo in the menu under the tab Model and click on the Edit button to set the parameters for the fiber generator. First, we define the size of the domain we want to model. For our example, we choose 1000 by 1000 by 100 voxels. Choosing the length of the voxel is not entirely free, since we have to model a certain fiber diameter distribution. This should ensure that even thinner fibers can still be sufficiently resolved. For this purpose, we use a measurement, which was also made available to us, in which the mean value and the standard deviation of the fiber diameter distribution were determined experimentally. As we can see from the distribution, it is roughly a log normal distribution. The largest peak is at about 0.2 micrometers. Since we want to model this large peak of fibers well, we choose a voxel length of 0.05 micrometers to ensure that most of the fibers are resolved with at least 4 voxels. This results in a total size of 50 by 50 by 5 micrometers, which we want to model. In this window, we can also define whether the fibers should be generated with or without overlap. Since our fibers are produced by electrospinning, we can allow the generator to produce the fibers with overlap. We also have to determine how many fibers we have in our microstructure. There are various termination criteria for this. Either a fixed number of fibers, a certain solid volume fraction, a grammage, a density, or an object rate percentage. We select the already pre-selected object solid volume percentage and set it to 17%. After we have set up our domain, we go next into the fiber options. By default, 2 types of fibers are selected as default. However, as these fibers are straight fibers, they are not suitable for our fiber structure. By clicking the Remove button, we remove them. To be able to choose the right fibers, we will have a look at the SEM picture again as a reminder. Although, as we can see, there are also straight fibers, there are also many curved fibers or fibers which are straight in sections and then curved again. We have to be aware of this when modeling our fibers. Therefore, we add 2 types of fibers under fiber type. First, we start with a curved circular fiber, which we can create by clicking Add. Now we can define various parameters for this fiber type, including the diameter distribution. Of course, we want to choose the diameter distribution according to the measured distribution. Remember, this was the distribution that was measured. So here, at the diameter parameter, we select Edit button and choose the log normal distribution. Here, we now enter the arithmetic mean of the distribution. And here is the standard deviation. Like a lower and an upper limit, since we have chosen a voxel resolution of 0.05 micrometer, our lower limit of the distribution should be greater than this value if possible. We can also choose an upper limit. If we look at our distribution, we choose 1.5 microns. Another parameter we still have to choose is the length. In our example, it is sufficient to choose a length that is greater than our domain. Since the domain we modeled is 50 micrometers, we choose a length of 100 micrometers for the fibers, so that, if possible, we have no beginning and end in our final fiber structure. The next parameter we can set is the orientation. For this, we have previously analyzed the orientation of the fibers. To be able to use it, we close the edit window shortly via the OK button. This saves the entries we have made so far. Then open the fiber orientations GDR file that we created earlier. A GDR file is a geodic result. Here we can find the orientation tensor we want to enter into FiberGeo. To do this, we click on the Edit button again and go to the Fiber options. We click on the Edit button, select Anisotropic orientation, select Orientation Tensor, and enter the values from the GeoDict result file. In the Z direction, we have no orientation analysis and therefore choose 0 for the time being. Now we click OK. With the parameter center, you can select an inhomogeneous distribution of the fibers in a fiber structure. However, this is not necessary for our example, and we leave it at the default setting. Since these are curved fibers, we have to determine the parameters for the curvature. For this, we click on the Curl tab and select the Curl mode Random. With the other modes, it is possible to model defined geometric shapes or use another method to model the curvature, which is still under development. First, we have to define the segment length. The segment length influences the generation process, because it can increase the frequencies that occur in the curvature. And on the other hand, if it is too high, it can lead to more or less angular fibers. In our example, we choose a segment length of 1, so that we do not get too high oscillation frequencies. The other parameters we need to enter are whether we want to use isotropic or anisotropic curvature parameters. If we use anisotropic parameters, we can enter the curvature parameters for each direction independently. Or if you choose isotropic curvature parameters, then the parameters are the same for each direction. Local straightness determines how much the fiber wants to maintain its current direction. If a low value is selected, the fiber retains its local curvature. The second parameter is global straightness. It determines how much the fiber follows the global orientation given for its type. If a value of 0 is chosen, the global orientation is ignored. If you choose a value of 1, it is always preferred. Randomness determines how much random deviation may be added to the direction defined by the previous parameters in each segment. As a rule, not a value too high should be selected here, otherwise the parameters selected above will lose their meaning. For our example, we choose a local straightness of 0.7 in the x direction, 0.3 in the y direction, and 0.1 in the z direction. For our global straightness, we choose 0.4 in the x direction, 0.15 in the y direction, and 0.85 in the z direction. For randomness, select 0.2, 0.25, and 0.05. As we can see from the values, we want the fibers to remain very much in the xy plane and not have a large curvature outside of it. Also, we want to have more curves in the y direction, and in the x follow the direction of the current fiber direction. This assumption is based on the fact that when we look at the SEM image again, we often see straight fiber areas, which then turn into a bend and then continue straight again. Such a behavior can be easily modeled by such a choice of parameters. Now, all parameters for our fiber type are defined and we want to save it. Therefore, we click on Save and choose a name, for example, Eardrum Type 1. If we take a closer look at the SEM picture again, we can see that there are many fibers that are very straight, so we would like to model these too. For this, we could add the type curved circular again and enter all parameters again. But since we only want to change the curvature parameters, we simply reload the type we just saved. This way we can get a copy of the Eardrum Type 1 fiber. Now we change the curvature parameters so that we get straighter fibers. For this, we increase the local straightness in all directions and also the global straightness. This means on the one hand that we want the fiber to follow the given orientation more closely and to maintain its current direction rather than its curvature, and on the other hand that we reduce the randomness. We have now entered all relevant parameters and can click OK. GeoDict now asks us if we want to generate both fiber types in equal proportions. Yes, we do. Then we can click on Generate. Now GeoDict generates the fiber structure. Now we see the fiber structure in the GeoDict standard colors red and green. In order to compare our generated fiber structure with the SEM image even better, we adjust the visualization to the SEM image. To do so, we click on the Structure tab and then on the button for the color and visibility settings, and color the fibers under ID1, ID2 and ID3 in gray. Then we click on the Camera tab and activate some post-processing effects that allow us to see more details like Show Outlines and Show Halo. Under the tab Structure, we can switch from the box renderer to the smooth renderer in structure mode. This allows an even higher contrast through the surface shaders, which allows us to see more fiber details. And we're done. We use GeoDict's image processing and image analysis tools to extract the necessary information from the 2D SEM image. With this information, we were able to create a digital statistical twin using these as generation parameters for FiberGeo. The result is an accurate statistical model on which we can now perform further property calculations. We hope you enjoyed this tutorial and thank you for your attention. And if you found this tutorial helpful, please check out our Math2Market channel for more GeoDict videos. Goodbye!